All right, welcome to another chance at doing this online classroom. All right, last class we talked about gravitational potential energy in our higher level class. And here I'm just going to give you a little bit of summary notes of what we talked about. Our main topic of what we talked about is at the top over here where we talked about how to calculate gravitational potential energy. And it gets just a little bit more complicated when we're taking objects far from the surface of the Earth, when we're not talking about these small changes like in that roller coaster on the left. We're talking about changes of 30, 40, 50 kilometers. It's not as simple. So if we're close to the surface of the Earth, like at this roller coaster, the gravitational field is pretty uniform. We're pretty close to the surface. And if the gravitational field is uniform, if I take an object from the bottom and I move it up, let's say 100 meters, the gravitational field strength doesn't change that much. So we were always calculating the gravitational potential energy of the work that we have to do against gravity in a roller coaster using that simple potential energy equals mgh. And we were plugging 9.81 meters per second squared being equal to g, and we were plugging that in there, able to calculate how much work we'd have to do against gravity at relatively small differences. But when we start to get a lot further away from the surface of the Earth, remember the surface gets curved, okay, the gravitational field strength starts to change. When we get to a point up here, g is not the same as it was down here. So if I plug 9.81 into that potential energy formula, I'm not going to get an accurate estimate of how much work I would have to do to raise an object to that height. So how do we actually do that? And that's the point of today's talk. It's actually pretty simple. All right, so in order to get there, we need to first talk about what the definition of gravitational potential energy is when we talk about it on a universal sense. We can't really talk about it, the work that we have to do to lift an object off of the ground, because G changes. So the definition is a little bit different. Gravitational potential energy is the work performed when bringing an object from an infinite distance away. So let's say the object is at over here, that's an infinite distance away, to a specific point, let's say over here, in a gravitational field, okay? And that work, how would I calculate the work that I have to do to go from an infinite distance to that point? Well, first of all, I need to know what force of attraction that object is going to have at that infinite distance. So the force of gravity is going to be equal to g m1 m2 over r squared. Now, if the object is an infinite distance away, now if I plugged infinity in for that r, you can imagine what's going to happen to that force. It's probably going to start to approach zero, but we'll get to that in a second. Okay, so how would I calculate the work that I'd have to do to go from here to there? Well, the work is equal to force times distance. Okay, so then I'd have to figure out how much work would I have to do to bring an object, pretty well to here. How much work would I have to do to put an object over there? If I subtract the two, I'd be able to calculate the work that I'd do to bring an object from here to there. Okay, so the formula becomes work is equal to force times distance. Okay, I can take a look at that as being R1. I can look at that as being R2. Okay, so if I try to calculate the work going to R1, let's see what that's going to look like. Work is equal to G M1 M2 over R1 squared times R1. R1 is the distance. Oh, look at that. R1 cancels out. So the work becomes G M1 M2 over R. Okay, so what I said is the total work that I'd have to do is to take the work that I'd have to do to bring an object from infinity to that point X in that field. Okay, so work is going to be equal to G M1 M2 over R1, which is actually infinity, minus G M1 M2 over R2. Okay, if I plug in infinity, so I'm going to erase this. If I plug in infinity over here, GM1 over GM1 M2 over infinity is going to become 0. So 0 minus negative GM1 M2 over R squared becomes negative GM1 M2 over R2. So that is the formula to be able to calculate the work I'd have to do to place an object at any point. So I just have to plug in the distance from the center of the object as R2 on the bottom there, and I'd be able to calculate the work that I'd have to do to bring an object from infinity to that point. So for example, here, I'm just going to erase all this stuff and we'll just do a simple calculation. Okay, I'm going to erase these lines too, just to make it clear. All right, let's just see how much work would I have to do to bring an object to, let's say, 1,000 kilometers away from the Earth. Okay, so work is equal to negative g m1 m2 over r. Okay, and let's say this object is 1,000 kilograms. The mass of the Earth is 5.98 times 10 to the 24 kilograms. Okay, so 6.67 times 10 to the minus 11, which is g, okay, times 5.98 times 10 to the 24 kilograms times 1,000 divided by r. R is 1,000 kilometers. Now I got to convert that into meters. So 1,000 kilometers multiplied by 1,000 will give me my meters. So it's going to be 1 million meters. Okay, once I plug all those numbers in, I should be able to calculate for what work is going to be. And let's see if you guys can calculate what that work is going to be. Okay. All right, moving on. When we talk about gravity, there's another way we can do it. Einstein kind of proposed that, well, what it actually is gravity, because it's very strange that matter would be attracted to each other. So we made a conceptual model, or he made a conceptual model. Well, maybe gravity is created by divots in space. Or if I put a heavy object onto a fabric, like you see on the left over here, what that guy did is he put a heavy object like a bowling ball in the center of fabric. It makes the fabric depress into a well. Okay, and any object that is moving in that well is going to start to roll down. Okay, so gravity could be caused by heavy objects sitting in a fabric of space. It creates a well, and that's a conceptual approach. How can we conceptualize gravity? The heavier that, if a light object sits in that fabric, it looks like that. If a heavier object than that sits in that fabric, like we talked about in class, it makes the well a lot steeper. All right, so you'd have to do a lot more work to raise an object out of that well than you would out of that well. Okay, so heavier objects would have a stronger gravitational field. The steepness of that well relates to the gravitational field strength. In fact, actually the gradient of that well would relate to the gravitational field strength. So something you would see in your text that we're talking about is how to conceptualize gravitational potential wells. What does that look like in space? Well, if you have a heavy object like a black hole in space, it would actually curve the fabric of space by sitting inside it and create gravity. And that's a theory. We think that there is some type of weird fabric in space that when you have heavy objects, they create a curvature, and we see light bending around it. There's a lot of interesting phenomena that could occur, and we have an idea that that could be caused by gravitational potential wells. Okay, so the steeper the well, the more work you have to get out, the stronger the gravitational field strength. We'll come back to these gravitational wells in a second. Okay, now another concept that we need to talk about in class was the idea of gravitational potential, which is not the same as gravitational potential energy as I showed you over here. Gravitational potential kind of relates to gravitational fields. A gravitational field is the force per unit mass. Well, a gravitational potential is the work done per unit mass, bringing an object from a point that is an infinite distance away to a point within a gravitational field. Why would I use a gravitational potential? Why do we even need that concept? Why don't we just calculate gravitational potential energy? Well, gravitational potentials allow us to just say that any object in this particular space, so if I have, let's say I have a mass of Earth, let's say this is Earth, any object placed at that distance would experience the exact same gravitational potential. They wouldn't have the same potential energy, but they would have the exact same potential, meaning they would have the same amount of joules per kilogram of energy at that particular point. Okay, so every object that is that distance away, now because it's spherical, okay, I can make a giant circle around that object. Okay, and any object that is following that circle, imagine that circle is a perfect circle, that is a fixed radius away. Any object that is along that circumference would have the exact same gravitational potential. It would take the same amount of work per unit mass to bring an object from infinity to that place. Okay, that many joules per kilogram. So how do I calculate that? Well, in the last problems up here, we were able to calculate work. Work is equal to G m1 m2 over r. That's my gravitational potential energy. I can call that EP, okay? On the other hand, to calculate the gravitational potential, remember it's work per unit mass, I have to bring over the m2. So my gravitational potential energy over the mass of that object is going to be equal to G m1 over r. So we just created another formula, okay? So gravitational potential is equal to G m1 over r. Okay, and this is inside of your inside of your data booklet, okay? And the symbol for gravitational potential, it's kind of strange. It's a capital V, VG, okay? Like volts, something that we used in the electricity unit last year. So VG is equal to G m1 over r. That's the gravitational potential. So I can calculate the gravitational potential at any point in a gravitational field. And if I set it over here, well, that corresponds to a circumference at that point. Any object on that circumference is going to have a gravitational potential. And why is that useful? Well, using gravitational potential, I'd be able to calculate the gravitational potential energy of any object at that place just by multiplying the gravitational potential times the mass of an object over there. So we often quantify gravitational fields and also in terms of gravitational potentials, because it's very, very useful to be able to calculate the work that you have to do to bring an object per unit mass to that place. Okay, if I take a look at these gravitational potential wells, okay, something else I can see over here is that at that point over here, I can draw a circumference. That's a gravitational potential, that circumference over there. And if I go a little bit further up that well, I'll make a larger circle. And that's what the gravitational potential would look like over there. And if I go over here, I'll make an even larger circle. As long as my object sits on that flat horizontal circle, it would have the exact same gravitational potential. And then multiplying the gravitational potential by its mass would give me the gravitational potential energy. Okay, so if I erase all this stuff, just to summarize what's in this box, okay? Yeah. All right, so VG is equal to G M over R. If I want to calculate work is going to be equal to VG, the gravitational potential, times the mass of the object. And that would tell me how much energy, potential energy I would have of an object if I moved an object to that point. Okay, so we just came across another formula. VG is equal to GM over R, and that defines gravitational potentials. Okay, so what you'd often see in a text, or if you look at images online, if you're trying to do a little bit more research on this topic, okay, if I'm trying to take a look at mapping out the gravitational potential around an object, sorry, this isn't working out for me that well. Okay, you would see concentric circles around objects. Okay, and each of these concentric circles represents a different gravitational potential. So we call this like V1, V2, V3, okay? And if I was an object at one of these potentials and I want to move out here, in order to calculate how much work I would have to do, all I'd have to do is take V1 minus V3, and that'll give me my change in gravitational potential. All right, and then if I multiply the change in gravitational potential by mass, that's going to give me how much work I would have to do to move from each of these concentric rings. Okay, so that's something that you would see in the text where they talk about gravitational potentials. Often they'll give you the potentials, okay? They would say that this is 1,000 joules per kilogram, and this is 10 joules per kilogram. And they'd ask you how much work would you have to do to go from V1 to V3. Well, you would subtract 1,000, 10 from 1,000, and you'd multiply by the mass, and that would give you the potential energy. Okay, so there's lots of practice problems over there. All right, now it's a good thing I drew these two objects by accident, because the other part that I wanted to talk about is what happens when I have more than one massive planet. What happens to the gravitational potential, or how much work I'd have to do? Okay, so let's say I was an object over here, right in between those two massive planets. Okay, well, how would I calculate the amount of gravitational potential energy that I would have, or how would I calculate the even the gravitational potential at that point? Okay, so around the other planet is also concentric rings. And these are all the gravitational, wow, doesn't seem to write over there. Now, because energy is scalar, it's additive. Okay, so the amount of work that I would do taking an object from infinity to place it here, it's going to be the work I'd have to do as if I had this mass, that planet on its own, plus the work I'd have to do if I had that planet on its own. So I'd be able to add the amount of work that I'd have to do in both of those instances. All right, so in the next episode, I'm going to talk about that. I'm going to stop this one here because that's a lot. So let's just kind of review what we have done so far.